Today, let's go into more detail about the electrical power system, or EPS schematic, that I showed you in my last video. So, let's get into it. I'm going to start over here with the solar cell hierarchy blocks, and then work my way over through the battery chargers, and then get down to the power management IC and load switches. I'm not going linearly through the schematic, since that would be really long. That's 39 pages of a lot of duplicate information, since each of these hierarchy blocks contain the same information, just with different refdes's. Hey, this is future me popping in for a second. This video got long, so I do have chapters listed below if you want to jump around to anything that you're specifically interested in. Thanks. So, looking at the solar cell connector, well, it's about as simple as this. It's just the connector itself, which at this point I've changed to just some through-hole mounting points to solder in wires to, and then I incorporated the diode in here, and then there's a voltage divider here for the ADC input into the microprocessor, since the solar cells could output a high enough voltage where I need to divide the voltage in half to not hurt the microprocessor, or the PMIC specifically. And to touch briefly on the diode, I chose, if we're operating at 0.2 amps on this line, then at room temperature we're close to nearly 0.3 volts of forward voltage drop, which is unfortunate but necessary when dealing with these sort of diodes. And I tried to strike a balance between getting this as low as possible and the reverse current of the diode, since there will necessarily be some leakage back through the diode if this solar cell is in the darkness and other ones are in light. I want to minimize how much leakage is coming through here. And as this goes down, this goes up, and vice versa. So this NRVB diode was a pretty good compromise based on what I could find on DigiKey. Now on to the maximum power point tracker. Luckily I was able to reuse this LTC3130 both as this maximum power point tracker and down the page as the 3.3 volt regulator as well. The way that I was able to do this was take a note of the VS1 and VS2 inputs. And based on how you hook these up to either ground or VCC, it'll change the setting inside the chip if it either wants to output 5 volts or 3.3 volts. Often chips do this with just a resistor divider, but the LTC3130 specifically has these sort of pull high, pull low option setting GPIOs to set the output voltage. Taking a look at the chip, it is a buck boost converter and has this capacitor inductor set up here. I tried to find a general value that would work for both the 3.3 volt and 5 volt output modes. So I think what I found is a pretty decent compromise for both of those, and really it seems like it would work over the whole range anyway. It's not much of a compromise. I did try to take care of adding a whole bunch of input and output capacitance, simply to eliminate as much noise as I possibly could. What we really care about is the maximum output current for VIN versus Vout, and for the 5 volt output, and my printer is pretty bad, but this is the 5 volt output line. And for the voltage in from the solar panel, we're always going to be in this sort of range from like 3 volts to 5 volts. So we're always going to be able to output at least 200 milliamps, which is what we expected the maximum output from the solar cells to be anyway, so no big deal there. For 3.3 volts, we're working with this line over here. When I get to it on the other side of the schematic, we're going to be input from the battery voltage, which works in this sort of range, and maximum output current that I would expect that 3.3 volt converter to draw is 300 milliamps, and so we're right within that range as well, so no problems there. Oh, and real briefly, here are these VS2 and VS1 output settings, so in theory I could output 1.8 volts up to 12 volts if I really wanted to. Moving on to the battery chargers, again I used the hierarchy sheets to duplicate how I charged and how I've written the battery for both of the batteries, which is just really convenient. And looking at the LTC 4066, which is my battery charger of choice, this battery charger has a built-in ideal diode, so the input in theory can work. I can, as long as I have a voltage on the input, it'll go right through to the output with even if the battery is not present, which is useful to have in the case that you either A, don't have a battery, or if you have a bad battery of some kind. It also means that the current from the input can be essentially combined with the current from the output. This will allow me to use as much solar energy as I can and essentially not use the battery unless I absolutely need to. Most of this circuit here is really just R's and C's to set up the proper usage of this chip. Up at the top, I have the 5-volt input that you saw from the other page. The most important things are just down here where I set the charge current, the input current, and the charge timer. The charge current I've actually set pretty low to only 50 milliamps. The input current is at most 0.1 amp, and the charge timer, which essentially is just based on however long your charge current is, works out to 136 hours. Plug it into this formula, comes out close to 4.7 UF. The reason I set the charge current to only 50 milliamps is because the solar cells might only output 200 milliamps, and there are 2 of these chargers. So if both of them are going, that's 0.1 amps, and I wanted to have some margin because we might not always be getting optimal conditions from the solar cells. Also, the input current itself is only 0.1 amps. That means from Vin itself, only 0.1 A max will ever come through. So on the output, from Vin to V out, only 0.1 amps is at most possible. But from the battery to output, I think it can do several amps. That is just the setup of its internal ideal diode. It's nice to be able to limit how much current is coming in on the input because I don't want this to look like a short circuit to the solar cells and essentially prevent them from ever outputting any useful amount of current. So hooked up right to the battery charger is the battery itself. And on this hierarchy page, I have 3 things. I have the battery heater control circuit, I have the NTC itself, the negative temperature coefficient resistor, and I have the battery itself. It is hooked up to a resettable, temperature resettable fuse, a poly fuse, and really, that's about it. It hooks right up to the battery charger that I just showed you. The poly fuse has a 2.82 hold current rating and will trip at 8 amps. Really, this is here for short circuit protection. Looking at the NTC, the idea is that I will hook this up to the battery. This will allow the battery charger to know if the battery is too hot and should stop the battery from discharging, or if the battery is too cold and it shouldn't charge. The hot point for this arrangement is 50 degrees C is too hot and 0 degrees C is too cold. Also, I don't think I have it on visible on the schematic, but this is a 10K NTC. So it's 10K here and 10K here. Then moving up to the battery heater control circuit. So essentially I have an op amp here, I have a load switch, and then some sort of connection to the battery to heat it up. Whatever that ends up looking like, I'm not exactly sure, but that's for future me to figure out. Essentially, I continue to use this VNTC circuit signal, which is some voltage generated by the battery charger. I don't exactly know what this voltage is, and I don't really care because all I really need is just the difference between, and the way that I use it for this comparator op-amp circuit is I take VNTC, which we can imagine is something like 4 volts, and I compare it, well, I divide VNTC by some fraction, and then I compare it to NTC. VNTC, looking down back at our NTC circuit, this is the bias voltage, and then NTC is whatever is the reading, whatever I generate from the thermistor itself. So I take that, this goes off to the battery charger circuit, and I use it again in this op-amp circuit. And as it works out, it's 73.7%, which is the same as the cold point. So essentially, if this ever gets to its cold point, this op-amp will turn on, which will turn on the FPF 2123, which will allow current to flow through whatever heater connection, whatever that ends up looking like. And yeah, I have it current limited to 150 milliamps, which is just a nice feature of this load switch. And that's about it. Oh, and the reason I need to even have this battery heater to begin with is because you cannot charge a cold lithium-ion battery. Well, you can, but you can only do it a couple of times. Charging a lithium-ion battery in cold conditions can damage it. So both of these batteries hook up into the ideal diode circuit, which is very simple. So this is the LTC4415. It has the diodes internal to it. I tried to pick a whole bunch of chips that had all of these internal diodes because I just didn't want extra excess components, even though you can find chips that are ideal diode controllers, which in theory can offer better performance, but I didn't want to have to deal with the hassle of picking extra components. The LTC4415 just does it for me, and I like that. Really, this is just a pass-through. VN1 and VN2 just both go in and both come out. There's some warning signals which do get passed to the power management IC, and otherwise I limit the current to 3.33 amps for each of the diodes because these just go right on through. So each of these are limited to 3 amps effectively, and this is something that I can easily tune if I want the current limit higher or lower or whatever. I think these go to 4 amps maximum. And looking at the ideal diode circuit, really this is just a wrapper for that LTC4415 because both of these V-outs are connected together, and I connect them together just through these 10 milliohm resistors so I can easily disable one side of the circuit if I want to during prototyping. Or I can also measure the current that's coming through the diode at this point. That's why I have a whole bunch of these 10 milliohm resistors, is just for debug purposes and development purposes. So I can either break a circuit if I know that something isn't working down the line here, I can just remove this resistor, and now I have eliminated this circuit entirely from causing any issues. In theory, in a final build of whatever I'm doing, these resistors would go away, but right now they're really useful for development. So V-bus goes right here, right to here. And that's the only place it shows up on the schematic. So the 3.3 volt regulator, this is the LTC3130, which I showed you just a couple minutes ago. It's arranged essentially the same as the 5 volt regulator. It also has the same power good load switch coming out of it. The 5 volt regulator is a little bit different since I could not use the LTC3130 for it, even though I would have liked to. And this 5 volt regulator I have picked, but I don't exactly have a usage candidate for it yet. I've picked this because I know I'm going to be using some sort of high power-ish radio. I mean, high power by it uses maybe 10 watts peak for a couple seconds, which based on my research seems to be pretty common. So I wanted 5 volts, which is just a generic enough voltage. I was hoping to find 3 amps, but 2 amps seemed like the most reasonable thing I could find in a package size for a chip that was easy to install. So let's take a look at it. This is the MPS MP3414A, which is actually in a TSOT package, so it has leads, it's easy to solder. I tried to pick as many parts on this board that were leaded parts, so I could actually easily hand solder them so I don't have to use hot air. There's a couple parts that I have to use hot air for, which is fine, but I wanted to make everything hand solderable because, at least for this first run of this board, I'm not going to have it assembled. I'm just going to do the assembly myself. This circuit is pretty simple. Really, there's just one inductor for this boost circuit. I tried to pick as large of an inductor, I think it was large, of an inductor as I could because I wanted to make the trade-off between size and amount of output current. According to the datasheet, if I could increase the size of the inductor, I could also increase the amount of output amps, which is what I want to get as much out of this circuit as I can. So here's the graph that's important. So input voltage, so at 4 volts, so 4 volts from our battery, we're at 2 amps output. So this isn't ideal. I would have liked to have a higher power chip, but this is what I'm working with because I know this specifically is cheap, it's easy to install, and hopefully should be easy to, well, hopefully I should be able to get something out of it. Maybe it's not exactly what I want, but it's a good starting place. Moving down to the bottom half of this board, the other big schematic that I haven't shown you is the power management IC. I said it was similar to the avionics board, and it is. If you look back at my other videos, you'll see that I'm also using an STM32L4, and in the other videos it had a whole bunch of other sensors that are not here, and that's for good reason because this is just for power management, and all I need is the CAN transceiver is the same, the debug port ends up being the same 32 kilohertz clock, and I still have the same MRAM memory. Otherwise, I have just a whole bunch of GPIOs. So these lines I've dedicated to interrupts. These I have set up for my on and off switches for my load switches. And then otherwise I just have some GPIOs. Now, when I was drawing this up, I just dropped in these 0 ohm resistors, which again are useful for development and debugging. If you want to isolate a circuit, you can just remove one, or if you wanted to wire up something else, you can do that by just removing a resistor or making a mod of some kind. Looking at the layout, these are hell. I don't know why I decided to do this, so I'm going to remove all of these, or at least most of them. Maybe I keep a couple in some certain circuits that maybe I think might not work or whatever, but I'm going to remove all these because there's so many and I do not need them, or do not need all of them anyway. And that's about it for the power management IC. Really, there's not much to it. Otherwise, I just hook up all the ADC lines I want, I hook up all the GPIOs and the interrupts and the on and off switches as I showed you in the last video. Not much to it, just a whole bunch of R's and C's. So on to the current monitors and load switching. This is what actually took me a while to get right, at least get it to a spot where I liked it. I don't know if it's really good. I haven't built it and tested it, but I hope it works. So this is the current monitoring and load switch page, or specifically it's current monitors with an S. So that's this page. And as you can see, it has just a whole bunch more schematics inside. So I use this page above the dotted line. I use this page for, these are all the 3.3 volt current monitors, and I use this page to essentially just set the current limits. So this one has a 3 milliamp current limit, and I also set the, and that's set based on this RF resistor and the shunt resistor. So these two you'll see get combined in an equation for an op amp to set the current limit. And then this I set here is for the load switch I use inside, which is the same FPF1213, which I showed you on the battery heater page, and I set the maximum current for this guy as well. Then under this dotted blue line, these are the quote-unquote high power circuits. So these are the 5 volt output. So in theory, I could have 2 amps coming out of that 5 volt converter. So I have these load switches, these TPS 270s, which are actually different from the load switches I use inside of each of these current monitors. And I don't actually monitor any current here. These are just load switches. So I was a bit lazy on the 5 volt ones, but I figure that any sort of high power circuitry would be on for a short amount of time anyway, so taking my chances with no actual current monitoring on these 5 volt load switches here. Anyway, let's get into one of these actual current monitors. I also spent way too much time making all of these schematics pretty. So voltage comes in here, and that's 3.3 volts for this circuit. It could be 3 volts, it could be 3.5 volts, it could be 2.8 volts or 2 volts or whatever, but I'm only using 3.3 volts for now. So This voltage comes in, it goes through a shunt resistor, and then goes into the FPF1213, where it's switched on, and it'll go to the output. That's the path, and there's a whole bunch of other stuff which will control this FPF1213. So another quick note, this VIO is the safe voltage for the PMIC, which happens to be 3.3 volts, but in theory I could run my STM32 at 2.5 volts or 2.8 volts or whatever, 1.8 volts, and then this IO voltage would make sure that I'm not plugging 3.3 volts into the GPIO of that STM part and accidentally hurting it. But anyway, effectively this is, again, 3.3 volts. So let's first look at the current monitor. So I have this shunt plus and shunt minus, which I also draw down here as the inputs into this amplifier. Now this amplifier has a gain of 500, so whatever difference around here is amplified by 500, and the output is input into this comparator. And this comparator, based on this RF voltage, based on this RF resistor, this has a 2.4 volt reference voltage that it generates, and I use that as a voltage divider to generate a reference voltage. And based on that reference voltage, I check to see if this gets too big, if there's too much current flowing through this resistor, this will just get bigger. So if this voltage gets too big, it'll end up going over the threshold. It'll cause this op amp to pull low. So pulling this op amp low will end up driving these two NMOS transistors low, and this actually is on here I labeled it my monostable pull down, or this is the hold off circuit. So this will pull down, so this goes low, this voltage goes high, which causes this to activate, or becomes low impedance anyway, causing this on signal to look like ground, which this is the enable signal, which will cause this to be off. So that's how the current monitor works and turns off that circuit. I also have an equation for this, so if you want, you can actually go through and calculate whatever shunt resistor you want and whatever reference resistor you want as well to get a whole range of different currents you can monitor. I also have this reset input buffer. So this is a buffer, and it has a reset signal, which essentially I have this buffer here because this is just a one-way valve. This reset signal is only ever an input, it's not an output. And I use that, so going back to the big page, I have these reset signals and I hook them up together, so single signal, such as the avionics external reset, can reset all of the avionics all at once, and that is all done through this reset buffer, as I call it. And this goes into the same spot that the op amp for the current monitor goes to, and it goes through the monostable pull down as well to affect the change on the input pin of the load switch. The other spot that this on signal goes is to the power management IC, and it of course has total control of if it wants to drive this pin low, disabling the load switch. Because by default, this load switch is pulled up high and it is on. One other thing that I'm considering doing is I have this DNP resistor here, which is from the output of this load switch, and this hooks up to the power bus that is used by the comparator, the amplifier, and this buffer. And currently this is hooked up to this resistor here, which is hooked up to VN, which should always have 3.3 volts on it. But the nice thing, if I remove this resistor and hook it up to, and instead install it here, so this is no longer a do not install or do not place, this is a 0 ohm resistor, then essentially this current monitoring stuff is all powered by the output of the load switch. So if it ever has an overcurrent event, it will essentially reset itself as well, which is useful because it itself could have a overcurrent event, which right now is not monitored. I don't exactly know if installing this resistor here will end up breaking something in this circuit in a way that I can't quite see. Maybe it can reset itself once, but it doesn't doesn't ever turn back on. I'm not exactly sure, so that's why I have the option of either this way of powering it or this way of powering it. Anyway, that is all for this circuit. It took me long enough. I really wanted to find a lot of common parts that I could use for monitoring currents for a whole bunch of different situations. I didn't want to have to pick different amplifiers or different comparators or a whole bunch of different stuff for a whole bunch of different situations. So that's why I'm happy to have this very generic solution. And although it has this big hierarchical page of a whole bunch of the same stuff, it allows me to reuse, which makes the design simpler and easier to read once you know what you're looking at. So that's it. That's all I have for the more in-depth dive. Hopefully that answers any questions any of you may have had, or maybe it just raises more questions. Anyway, I am making progress on the layout. I'll drop that in here. I've picked a 8.5 by 8.5 centimeter frame. So I'm going to try to fit everything I have onto those 8.5 by 8.5 centimeters. And right now it's looking like maybe I can. There's still a lot of questions of how much massaging I need to do to make everything fit. I have decided, I realized this pretty early on, that of course I'm going to need a 4-layer board in order to do this, which is fine. I was originally hoping, and maybe this was totally foolish, hoping to have everything fit on that size board and it'd be 2 by 2 layers. But going over all of these components, and because I have 16 power rails, there's just a lot of resistors, there's a lot of capacitors. My decision to make all these parts easy to solder means that they're bigger, and that just means they take up more space. But because I want to assemble this at home, that's what I decided to go with, and well, I think everything will fit. Anyway, thanks for watching.